Hello, welcome to S Chemistry. I am your instructor Dr. Suhas Gauri and I will be teaching BSc 5th semester Physical Chemistry course on colligative properties of dilute solution. Here is the outline for this lecture. So first I will introduce about how to calculate or determine the molecular mass of the solid from the elevation of boiling point. So it's an application of colligative property. So secondly, Landsberger-walker method. So this is a apparatus to measure the vapor pressure or elevation of boiling point. So let's start with determination, how to determine the molecular mass from the elevation of boiling point. So from previous lecture we are continuing. So delta T is directly proportional to the P minus Ps. So here this is equation number 1 where delta T represents the difference in boiling point, that is elevation of boiling point, and P minus Ps, that is represents the lowering of vapor pressure. Since P is constant for the same solvent at a fixed temperature, from equation 1 we can write that delta T is directly proportional to the P minus Ps divided by P. So this become equation number 2. So this indicates that we are lowering vapor pressure divided by P is proportional to the difference in boiling point. So but from the Raoult's law for dilute solution we get this equation P minus Ps divided by P. So this is directly proportional to the W into M divided by capital W into M. So here this gives the equation number 3. So here this equation 2 says that temperature is directly proportional to the vapor pressure of the solution, and from Raoult's law we can say that vapor pressure is directly proportional to the depends on the number of moles of solid. Since M, that is molar mass of the solvent, is constant from equation 3, we get this equation number 4, that is lowering of vapor pressure. This term represents the lowering of vapor pressure is directly proportional to the moles of the solid. So P minus Ps divided by P is directly proportional to the small w divided by capital W into M, that is equation number 4. So from 2 and 4, delta T is directly proportional to the W divided by M into 1 by W. So if you equate equation 2 and 4, we can directly get equation number this equation. So this says your difference in temperature is directly proportional to the moles of the solid. So if you make this as an equation, so Kb will get as an extra constant, that is we call it boiling point constant or ebullioscopic constant of molar elevation constant. So here equation number 5 gives the constant, that is boiling point constant or ebullioscopic constant of molar elevation constant. If your small w divided by m, that is number of moles of solute, is equal to 1 number of 1 mole, then your capital W, that is the weight of solvent, is 1, then your Kb is equal to the delta T. So from that you can calculate the value of, so that equation says that molar elevation constant may be defined as the boiling point elevation produced when 1 mole of solute is dissolved in 1 kilogram, that is 1000 gram of the solvent. If the mass of the solvent, that is capital W, is given in grams, it has to be converted into kilograms. Thus the expression 5 assumes the forms. So here delta T is equal to the Kb into W divided by M into 1 by capital W divided by 1000. So this become equation number 6. So M equal to 1000 into Kb into W divided by delta T into capital W. So this become equation number 7. So equation 7 you can directly use for the, if your all amount that is like mass of the molar mass of the solvent or mass of the solute is given in the gram, you can follow the equation number 7. So here delta T is equal to elevation of boiling point, Kb is represents the molar elevation constant, small w that is equal to like mass of the solid that is in the gram, capital W represents the molecular mass of the solute, and capital W is represents the mole of the solvent, mass of the solvent, so that is in the grams. So what is the unit of Kb? So from equation 6 we can generally say that, so your delta T can be represented in terms of either degree Celsius or Kelvin, and your weight of the solvent is represented in kg. So divided by this number of moles. So unit is Kelvin kilogram per mole or degree Celsius kilogram per mole. Now the constant Kb, which is a characteristic of a particular solvent used, can be calculated from the thermodynamically derived relationship, that is Kb equal to R into Tb square divided by 1000 into Lv, where R equal to gas constant, Tb equal to boiling point of solvent, so Lv equal to like molar latent heat of vaporization. So thus for water R equal to 8.134 joule per mole. So that is your gas constant, where T represents the solvent boiling point, that is 373. So here we are calculating for the water. So Lv represents the latent heat of vaporization for water, that is 2260 joules per gram. So if you put all this value in this equation, so you finally get the Kb value, that is 0.52 Kelvin per kilogram. So that is the value of Kb which is calculated from this equation. So this equation comes from the thermodynamic derivation. Now we will see Landsberger-walker method. So like apparatus part. So this is the basic diagram of Landsberger-walker apparatus, where so this method was introduced by Landsberg and modified further. It's modified by Walker. So this name of scientist who invented this apparatus or method to calculate the uh, vapor pressure. So here the apparatus are the graduated tube. So as you can see in this picture figure, you have this outermost covered tube is, that is graduated tube. So the purpose of this tube is an inner tube graduated in milliliters with a side hole. So this is your graduated tube. So graduated means from lower to higher you have these all marks. So if you have solvent in this tube, you can directly say the volume of the solvent. So here hole is given just to, like, whatever the excess vapor is there, that should come out very easily. Then second is the boiling flask, that is not shown over here, but from that boiling flask you are directly getting the boiling solvent vapor. So it contains the pure solvent and it is equipped to the send solvent vapor through a rose head, a bulb with a multiple holes into the graduated tube. So from this boiling flask you are getting boiling solvent vapor, and that vapor is coming into the this graduated tube with the rose head. So rose head has the multiple holes, so your all vapor coming out through this hole. Then we have the outer tube, so that is to receive the hot solvent vapor coming from the side hole of the inner tube. So whatever the hot air is there, hot solvent air, vapor is there, that is coming. So this tube has only work is to receive the hot solvent vapor, and we that has to get condensed. And another apparatus is the thermometer. So the thermometer which reads to like minimum temperature you can record, that is 0.01 Kelvin, and it is dipped into the solvent or solution inside the inner tube. So inside you have either solvent, pure solvent or solution that we have to measure. So the minimum you can measure up to 0.01 Kelvin. Now the procedure we will see how we are going to calculate. So first we will prepare and first we will prepare solution and solvent, and we will measure the initial measurement. First we have to fill the graduated tube with the pure solvent, followed by you have to pass the vapor of the same solvent that is in the boiling in the separate funnel flask into the graduated tube using the rose head. So this vapor will condense and transfer its latent heat to the solvent, causing it to boil. So at first at room temperature it will not boil, but after some time as you pass through the solvent vapor, it will start gradually, it will start the boiling due to latent heat of the solvent. So once the solvent begins to boil, then we and temperature stabilize, we have to record the boiling point temperature of the pure solvent. So that will be the your first reading. So this is your first reading, that is TS, that is for the pure solvent. Then adding solute. So then we have to add the solute to make a solution, that is your interest of your solution. So temporarily stop the vapor supply, then you have to wet the palate of the solute and then drop it into the solvent inside the inner tube. So restart the vapor flow, continue passing vapor through the inner tube until the boiling point of the solution stabilized. So after putting that solvent or solute into the solution, we have to restart the vapor flow. So continue passing vapor through the inner tube until the boiling point of the solution stabilized. So record this new constant boiling point temperature as the second reading. So that is the T solution. Then we have to do the final measurements. So first we have to cut off the supply of the pure solvent vapor, then raise the thermometer and rose head out of the solution. Then we have to measure the volume of the solution from that left in the graduated tube. So from that graduated tube you can directly measure how much volume is there in that graduated tube. Then you have to record this volume as your third reading, and from that volume you can directly calculate the weight of the solvent. So this Landsberger method is to calculate the molecular weight of the solute by using the expression. So from given expression we have this M, that is molecular weight of the solute, that is equal to the 1000 into kb into small w, that is divided by delta T into capital W. So using this expression we can calculate the molecular weight of the solute. where delta T represents the elevation of boiling point that we can get from this experiment, that is Landsberger-walker method. So using these apparatus you can get the delta T. So Kb is specific to the solvent, and that we have the value, that is molar elevation constant, and weight of the solid we know, that is in the gram. So, and weight of the solvent, that is the third reading we can get from that. So volume into density we can get weight, or you can directly measure by weighing balance. So all these four parameter we know, then fifth parameter we can definitely we can tell. So that is your molecular weight of the solid. So that's how we calculate the molecular weight of the solid. So here we come to end of this lecture, and these are the references for the images, and for this content you can follow these three books. So thank you for kind listening. See you in next lecture. Till then, happy learning.